So I simply said that the cutter joint has three basic members. We have the spigot end, we have the cutter itself, and then we have the socket end. We also have the rod end. This is called the rod. Okay, this is the rod end. So this is the cutter itself. This is a three-dimensional view of what a cutter looks like. Now, for shear failure, about four segments of the cutter undergoes failure by shearing. The first segment is, first of all, we consider the distance between from one end of slot to the spigot itself, and by failure, the shear formula is simply given as shear stress equals to the load all over 2 times d1 times area, times A. A now becomes the distance between one end of the slot and the spigot itself. All right, so we consider the failure of what shearing due to what the shearing failure in the spigot end, and then we'll find this distance. So the first thing to do is to what design this distance between the spigot end and the slot itself. The next thing to also consider is the shearing failure of the socket. The shearing failure of the socket is simply given mathematically as this: shear stress equal to P all over 2 times D2 minus D1 times C, where C is what the thickness of the socket. So all we need to do now is to what design the thickness of the socket. So we simply make C subject of the formula from here. So when the question says design is cutter joint, it is simply telling you what you are basically designing is simply either you're designing distance or diameter or thickness, just to avoid any form of failure. That's the essence of designing, not one big thing or the other. All right. Now, the next failure or the next component that occurs by failure is the design of the thickness of the spigot itself. The thickness of spigot from the formula is given as this: shear stress equals P all over pi D1 times T1. So all we need to do is simply make T1 subject. This becomes the thickness of the spigot. So we make T1 subject. We'll be given a shear stress. If we are given a shear stress, of course, you put in the value into the equation and then you obtain the value of formula for your T. And finally, we design the width of the cutter, and the width of the cutter, of course, that could be seen from here. This is the cutter, the aspect of the cutter now. This becomes the width. This is the thickness of spigot, and this is the width B from the three-dimensional view. So we design the width of the cutter, and mathematically it is given as shear stress equals P all over 2 dt. So all we need to do is simply make the width subject of the formula, and we are good to go. Then I said that if the cutter material is made from steel, if the cutter joint is made from steel materials, then we have these approximate values. First, D1 is equal to 1.21D, D1 equal to that, capital D1 now equals 1.25D, T itself equals 0.3D, and D2 equals 2.4D. So we are going to employ this in solving this particular problem that is given to us. So someone can read the question now for me, please. Biggie, after now, discuss with him. Please, someone should read the question for me. Check your past question. First of all, the cutter joint is made of steel. Go on. Okay. Given P is equal to what? 720 kilonewtons. Permissible shear stress is given as what? 150 meganewtons per meter squared. Okay, so we are asked to design the cutter joint if the cutter joint is susceptible or can only fail by shearing. And I've said if a cutter joint fails by shearing, then we'll have 3 or 4 components inside the cutter joint which fails by shearing, which are being listed on the board there. So what we'll do now is I'm going to wipe all this side out now. Then we'll start analyzing using all these formulas. So the first thing to design is design of what? Okay, distance from one end of the slot to the spigot. So let's start with that. Now, first of all, we need to find the value of this D. We've said that D1 is actually 1.21D, and if you notice, all of them are actually related to what? This D. What then is this D? Recall that shear stress Recall that shear stress is actually force all over area, and this is equal to force all over area is simply given as pi over 4 diameter squared. So from here we can find the value of that D. We were given the shear stress, we are given the load itself P. P was given as 720 kilonewtons, still the same as F. So therefore we simply make D subject of the formula. To do that, of course, shear stress was given as 150. So you have 150 by 10 to the power of 6. Remember, this is 150 meganewtons. Is same thing as saying 150. Mega is by 10 to the power of 6. You have this. So this is 150 by 10 to the power of 6, and that's equal to the force was given as 720 kilonewtons. Kilo simply means 720 by 10 to the power of 3. That's kilo. That's 1000. So you simply have 720 by 10 to the power of 3 all over pi over 4 diameter squared. So from here, all we need to do is simply cross multiply. Let the whole of this term multiply this. We need to make d squared subject of a formula and find the value of d. So we simply cross multiply. The whole of this value multiplies 150 by 10 to the power of 6. So you have 150 by 10 to the power of 6 multiplied by pi over 4 d squared, and that's equal to 720 by 10 to the power of 3. You have this. Okay, so from here, of course, from here, 150 can divide by 4. It becomes 150 by 10 to the power of 6 pi all over 4 d squared, and that's equal to 720 by 10 to the power of 3. Okay, so please give me 150 exponential 6, or just give me 150 divided by 3 by 4. 37.5 by 10 to the power of 6 pi diameter squared, and that's equal to 720 by 10 to the power of 3. So from here we can make d squared subject. D squared is now equal to, it becomes 720 by 10 to the power of 3 all over 37.5 by 10 to the power of 6 pi. Okay, so please give me this value. D square equal to, so don't forgetting, 720 exponential 3 divides 37.5 by 10 to the power of 6 pi. Okay, pi is something as saying this is 720 by 10 to the power of 3 all over 37.5 by 3.142 by 10 to the power of 6. So that's what you give to me first. 720 by 10 to the power of 3 all over. So give me 37.5 times 3.142. 37.5 times 3.142. 117 point. So we have 117.3825 by 10 to the power of 6. So give me this division now. 720 exponential 3 divides 117.825 by 10 to the power of 6. 6.11 by 10 to the power of minus what? Minus 3. So we can actually find the value of D simply by taking the square root of both sides. Therefore, D is simply equal to the square root of 6.11 by 10 to the power of minus 3. Give me D. 0.07, 0.078 in meters. Okay. So the value of D, let me state it here. D is actually 0.078 in meters. So obtain the value of D, we can now start our design. Now, what's the first thing to design? Okay, it's here. Distance from end of slot to the spigot. Alright, so that's the first thing to design. I can wipe here, right? No? Alright, so distance, design of distance from end of slot to the spigot. So we have this. All we are looking for now is to design the distance A. Okay, so we simply make a subject. If you make a subject, you are simply going to have that A is equal to P all over 2 times D1, okay, times shear stress. This becomes the formula for A. So we need to design the distance between the spigot and, of course, the end of the slot, which is simply A. We make a subject, which is here from isometric view. So we make a subject, it becomes P all over 2 D1 times shear stress. But what is D1? Numerically, D1 is given as 1.21 D, and we've obtained the value of D as this. So we can now compute D1, okay, but D1 equals 1.21 D. That implies that D1 itself is now equal to 1.21. D is simply 0.078. 0.078. Please, see him. Alright, so this simply implies that D1 is equal to, give me this value now, 0.094. 0.094, what? Okay, like this, in meters. So that gives us D1. D1 is, yes? The answer what? D2? I'm looking for D1 now. This is D1. And I said D1 numerically is 1.21 D. And we've obtained the value of D as 0.078. So simply multiply the two of them. D1 is 1.21 D, which is 1.21 times 0.078. And you gave me this as the answer. So this is now D1. All we need to do is now design this distance A, and that's equal to the load was given as 720. You simply have 720 by 10 to the power of 3 all over 2 times D1 now obtain 0.094 times shear stress 150 by 10 to the power of 6. So do all of this together and give me the value. That means that distance A is equal to, okay, please give me the value. 2, be very careful, oh. This is times 10 to the power of 6. 2 multiplies 0.094 multiplies 150 exponential 6. Divide 720 to that value, or by that value. 0.026 a meter. So this becomes the distance of distance from the slot to the spigot end. So that's the first thing to design. Design the distance from the slot end to the spigot end, and that distance is simply given as A. So you make A subject from the formula, you have this value. That becomes A. First design done. Next thing to design from what I gave you, what was that? Alright, so from what I gave you, what's the next thing to design? Of the socket end. So we are designing thickness of socket, right? We are to design thickness of socket. So design thickness of socket. Design the thickness of socket. Thickness of socket. And the formula is given as shear stress is equal to P all over, that's D2 minus D1, right? Multiplied by C. So the thickness of socket is simply C, as can be seen here. That's the thickness of the socket, C. So all we need to do is make C subject of the formula and times 2. 2 like this. Okay. So we have 2 into D2 minus D1 times C. So all we need to do is to make C subject of the formula. And if we make C subject, which is the thickness of the socket, C becomes equal to P all over 2 into D2 minus D1. So all we need to do here now is solid times shear stress times shear stress, yes. So that becomes the formula for the thickness of the socket. So all we need to do is simply obtain the value of D2 and D1. And from numerical values, if the cutter is made of steel materials, we have that D2 is actually 2.4D. So therefore, we find D2. D2 is equal to 2.4D, and that's equal to 2.4. We calculated D as simply 0.078. So 2.4 times 0.078. What's D2, please? 0.19. And next is D1. D1 itself, okay, we've done that before. D1 gave us 1.21D, which is 0.0. D1 is 1.21D. And we obtained this value previously here as 0.094 meters. So you simply have 0.094 in meters. Okay, so we now compute the value for the shear stress. Shear stress tau is now equal to the force. The load was given as 720 kilonewtons. Same thing, 720 by 10 to the power of 3 kilo all over, we have 2 times D2 minus D1, and D2 is 0.19. You have 0.19 minus D1, 0.094, 0.094 times shear stress, times the shear stress, which is 720, right? Okay, 150, which is 150 by 10 to the power of 6. So do all of these values and give me the value. This is supposed to be C, please. That's C, thickness of the cutter. So give me the value C. All right, so C equals 0.025 in meters. So this becomes the thickness of the socket. Yes, see, that's the thickness of the socket. So after designing thickness of socket, so what's the next thing to design? Of the spigot. Okay. I can wipe here, right? Oh yes, take your time and write, please. All right, so next we design the thickness of spigot of socket. This is socket now. Next we design the thickness of spigot, and the spigot also undergoes shear failure. What's the formula? Shear stress equal to P all over pi D1 T1. Okay, so we design the thickness of the spigot given by shear stress equals P all over pi D1 T1. So we simply make T1 subject, that's the thickness of the spigot. So, all right, so if we make T1 subject, we are going to have that T1 is equal to P all over pi D1 times shear stress itself. Okay, and we already obtained the value for D1. D1 is given as 0.94, where D1 equals 0.094 in meters. That simply implies that thickness T is equal to, first is P. P is given as 720. So you have 720 by 10 to the power of 3 all over pi is 3.142 by D1 0.094 by shear stress, which is 150 by 10 to the power of 6. So this simply implies that the thickness T1 of the spigot is simply equal to, evaluate that and give me the value. 0.016 in meters. This becomes thickness of the spigot. And we have one more thing to design. That is what? The width. The width of the cutter, right? Yes, width of cutter, B. So we have to design the width, B. Can I wipe here? Finally, design the width. Design the width. The width of cutter. And the formula is simply shear stress is equal to P all over 2B, 2BT, right? Please confirm. Or is it T1? 2BT. All right. So the width is actually B. We simply make B subject. If we make the width subject, B is now equal to load P all over 2 times shear stress times T. So we make B subject and we have that. But from numerical value, okay, T is equal to 0.3 D. And this is equal to 0.3. D was given as what? 0.078. 78. So this actually implies that T is equal to what? 0.023 in meters. So we can now find the value of the width. Therefore, B, which is the width, is now equal to load 720 by 10 to the power of 3 all over 2 times shear stress 150 by 10 to the power of 6 multiplied by the thickness 0.023. So you have to be careful. It is not T1. It's not T1. It's actually T. So they are different, not T1. So give me this value now. Therefore, width 0.104 in meters. And there ends the answer to that question. Second question. So that's how you design a cutter joint when it undergoes shearing. So cutter joint majorly undergoes 3 kinds of deformation. It can fail by crushing, it can fail by tension, it can also fail by shearing. Okay, so among these 3, the question specifically said calculate the failure of the joint by shearing. So which means we're only going to consider the aspect of the cutter joint which undergoes shearing deformation or shear failure. And those 4 are actually what we need to design to prevent failure by shearing. All right. Question 2.